Welcome back to ECE 441A 541A. In this video, what I would like to do is work through a few of the different cases that are possible with the Routh array, and so this is a session we're calling Routh array examples. We'll deal with three different cases. The first case, which we've labeled A before, is if our left column of elements in the Routh array are all non-zero, then we can determine, based on the number of sign changes that occur in the left column, how many roots we have in the with positive real parts or that are in the right half plane. The second case, case B, is if we have a zero left column element with other entries in that row or other elements in that row that are non-zero, then we'll insert this epsilon into that left column element and continue the construction of our Routh array. That's case B. And in case C, when we are confronted with an all-zero row as we're building or constructing the Routh array, that actually means that we have symmetry with respect to the origin of the roots of our polynomial that we're using to build the Routh array with. That being the case, we have to identify an auxiliary equation, differentiate that, and use the result of that differentiated auxiliary equation to populate that all-zero row, and then we continue with the construction of the Routh array. Let's get started by simply establishing some notation. The notation is we will just use a subscript on the coefficients consistent with the power of s. Here we have a sub n, s to the n, plus a sub n minus 1 multiplied by s to the n minus 1, and so on, down to a sub 1s plus a sub 0, where a sub 0 is our constant coefficient, or it's the coefficient that is scaling the s to the 0 power, and obviously then that's the constant coefficient in our polynomial. We can now construct the Routh array, and the first two rows of the Routh array come directly from the given polynomial. And we can, if we want, establish some notation or bookkeeping to help us with this process of construction by saying, oh, I have an nth order polynomial. I'm going to have an s to the n row in the Routh array. I will then create that top row by picking off a sub n, the coefficient of s to the n, and then I'll step over the next power of s and go to the subsequent power, which is a sub n minus 2. I'll skip over the a sub n minus 3 and pick up the a sub n minus 4, and I keep skipping over alternate powers of s until I run out of coefficients. I've now built up the first row in my Routh array. The second row, s to the n minus 1, is created similarly, except we now simply step one power down in terms of the polynomial of s. We pull off the coefficient associated with s raised to the n minus 1 power. That's now the a sub n minus 1 coefficient. We start jumping over alternate powers of s, and that means then that the next column entry in the second row is going to have the coefficient associated with s raised to the n minus 3rd power. So that's going to be a sub n minus 3, skip over a sub n minus 4, pick up the a sub n minus 5, etc., until we run out of coefficients. The first two rows of the Routh array construction are available to you from the given polynomial. After you've now introduced or inserted those coefficients in the correct locations, now we can complete the construction of the Routh array using those two rows to begin with. And we will then compute B1 we will compute B1 by taking a sub n and multiplying it by a sub n minus 2 minus a sub n times a sub n minus 3 all over a sub n minus 1. So we're always working with the two rows immediately above the row that we're trying to construct, and we're always working with the left column entries as we build more and more terms. So B1 is built from those four elements. B sub 2 would be also using these two elements in the left column, but it now goes one column to the right and uses those, so it now has a sub n minus 1 times a sub n minus 4 minus a sub n times a sub n minus 5 all over a sub n minus 1. And we just keep doing that. B sub 3 would use this entry, or that column of elements in the two rows above. For the C's, we go again two rows above and do exactly the same strategy for creating the C entries in the S to the n minus 3 row. This will be a little bit clearer when we go through some actual examples. And as we go down, again, we have our bookkeeping notation on the left, keeping track of all the S's. In the S2 row, we'll have two non-zero elements, possibly, but we'll have two element locations in the S sub 2 row. S1, we will simply have one element left that's the coefficient associated with S to the 1 after we've built everything up, and then we would have our last coefficient in the Routh array being W1, but because W1, in this case, W1 is now V1 times U sub 0 minus U sub 2 times this 0 element, or this empty element, divided by V1, you can see that that's always going to, when you have this empty element, that U sub 0 here will immediately slide down and become the U sub 0 element, or the element in the S to the 0 row. So that's kind of a shorthand or a short path to obtaining the constructed element in the S sub super 0, or the constant row in the Routh array. Let's look at some examples. We've already done this example. Let's just repeat it quickly. This is a monic second order polynomial. Monic meaning we now have a coefficient of 1 in front of the highest power of S, which is S squared for a second order polynomial. And in this case, we realize that the Hurwitz test, A1 and A sub 0, those are present. We don't know maybe whether or not they're positive. Those are just coefficients. If we plug that into the Routh array, we have the S squared coefficient, that's 1. We skip over the S coefficient and pick up the A sub 0. The next row down, we simply move one power down from the highest power, and that's S, and its coefficient is A sub 1. We jump over the S to the 0 power, and we're out of coefficients, and that's why I'm giving you this dashed red element showing that that particular element is 0 in the Routh array. To build up or to construct B sub 1, we now take A1 times A sub 0 minus 1 times the empty element, which is 0, divided by A sub 1, and that now allows A sub 0 to pop out. And as we just said, at this point in the Routh array construction, that A sub 0 just will slide down, and we really don't formally have to go through and show every time that B sub 1 actually is replaced with an A sub 0. For stability, we want no sign changes in the left column. 1 is a given as positive. That's in the first row. The S1 row A1, we want that to be actually we want it to be positive, and we want S sub 0 to be positive. So the Hurwitz test, which is really present and positive, that, based on the Routh array, is now a sufficient condition for second order polynomials. So if you're given a polynomial s squared plus a1s plus a sub 0, if you can force a1 and a sub 0 to both be there, present, and positive, then you know that the roots of that quadratic will be in the left half plane. That's what that says. Let's now look at one more example that might illustrate case B. And this one now has a polynomial. It's a fourth order polynomial, s to the fourth plus 5s cubed plus 40s squared plus 180s plus 144. If we apply the Hurwitz test, we're looking for s4, 3, 2, 1, 0. We have all of the terms. They're present. They're also all positive. So now we've passed the Hurwitz test, but really all that says is, okay, we don't know exactly, or it's not sufficient to give us any information other than we can't conclude that it's definitively unstable at this point. So now let's build up the Routh array associated with this particular polynomial. And to do that, let's go ahead and start with the first two rows, and I will build those now with 1. I'll skip over s cubed, put in a 40, I'll skip over s, and I have a 144, and I'm now out of coefficients in the s to the fourth row. S cubed, I now say, oh, that's s cubed, so I'll pull down or insert the coefficient of the s cubed power. Then I skip over s squared, and I have 180. I skip over the constant, and now I'm out of terms, so there now is an empty element that probably will be useful in the completion of the Routh array. Let me now build up this Routh array, B1. Let me do it here on the side so that you can see where these are coming from. I have 5 times 40 minus 1 times 180 all over 5. So now I have 5 times 40, that's 200, minus 180, so the numerator now is 20, divided by 5. This now becomes a value of 4 for b sub 1. If I'm now computing b sub 2, I'm using 5 with 144 minus 1 times nothing. So now I have 5 times 144 divided by 5. So this now becomes 144, and I knew that really was going to result because I had this empty element sitting underneath the 144. Now let me continue and build the S1 row of the Routh array. Now let me say that this is C sub 1. C sub 1, I now take 4 times 180 minus 5 times 144 and divide by 4. Or I now have 4 times 180, that's 400 plus 320, splitting that up a little bit, or that's 720. I now have 5 times 144, if that's now 5 times 100 plus 5 times 40 plus 5 times 4 is 20, so that also is 720. So my numerator, in fact, in the C1 is 0, so now I have this C1 value being 0. And that's now an all 0 row. So this is now, since there's nothing going to be here, that's not even existing, so now I have an all 0 row in the Routh array construction. I can't continue because I would have to be then dividing by that C1, which is 0, in order to build up this last entry, and I can't divide by 0. So now I need to introduce an auxiliary equation, and that's now going to be A of S, which comes from the elements in the row 1 above the all 0 row. So now I'm pulling down the expression that I can build from the S squared row, and that's now 4, and since that's in the S squared row, that's what's helpful about having this bookkeeping. And then remember what happens. I now skip over a power, so I don't have a S term, but I do have a 144. So now my auxiliary equation is 4s squared plus 144, and that's I found from the S squared row, which is the row immediately above the all 0 row. Now, in order to populate the S1 row to replace that all 0 row, what I need to do is differentiate this auxiliary equation with respect to S. I end up with 8s plus 0 using my calculus. And now I can say, oh, now in fact I can replace that 0, the all 0 row, with an 8. So now I have an 8 here for my all 0 row, and I can continue the construction of this Routh array table. So now I have 8 times 144 minus 4 times nothing divided by 8, or I now have 144 as my entry. And in fact, you could have anticipated that because it was coming down through this empty element location. So now I have my Routh array built, it's constructed. What can I say about sign changes? In this particular case, I have a positive, 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 positive. There are no sign changes. So from this Routh array, I see I have no sign changes, and that says I have no roots with positive real parts, or no roots in the open right half plane. But there was an all 0 row in the construction. Remember, the S1 row was 0, and that now tells me that I actually have a flag that I need to keep track of. I now had an all 0 row, and that produces a flag, that raises a flag. So now I know that because of that all 0 row, the system actually, that polynomial that I started with, the system has roots that are symmetric with respect to the origin. And what row was all 0? The S1 row was the 0 row, and that now says that I can look for symmetry of my roots based on the row one above the S1 row. So the symmetry in the original polynomial can be determined because I now am saying, oh, there was symmetry from one row above, which was the S2 row, and now I can look at what I have. I can say, or there was symmetry of two roots. So I now am concerned with what's going on in the S2 row. And if you're thinking about what do I have in the S-plane, potential patterns of two roots that are symmetric with respect to the origin, I could have a pole here and a pole there, or I could have a pole there and a pole there. Those are both supposed to be equidistant from the origin. So this is what I have in general for those two possibilities. When I have symmetry of two roots with respect to the origin, coming from the S2 row, but in our case, remember, I actually had no sign changes, so I didn't have any root in the right half plane. So you can sort of already determine that this left picture or this left case is not what we have for this situation. It is going to correspond to having purely imaginary, but we can find that those symmetric roots by looking at the s squared row. And the s squared row was 4s squared plus 144 equal to 0. That says if I divide out a 4, I have s squared plus 36 equaling 0, or s squared is equal to minus 36, or s is now plus and minus j6. So now that is more information than what I had from just saying I had no roots that had positive real parts, but the fact that I had an all zero row told me that I had symmetry. That raised this flag that says, oh, there's symmetry with respect to the origin, and that symmetry is going to be found by looking one row above the all zero row. So I'm now looking at the s squared row. I have a coefficient of 4 scaling s squared. I have 144 scaling s to the 0. That now gives me the polynomial whose roots would give me the roots that are symmetric with respect to the origin. That's example number 2. And now let's look at example number 3. Of s cubed minus 3s plus 2. So in this case, if we were just worried about stability, or if our system is stable or not, the Hurwitz test, actually we have a missing s2 coefficient. So we have one coefficient that's not even there, it's not present, and we have a negative S1 coefficient. All it would have taken was one of those, but it now, with that, it fails the Hurwitz test. So we know that this particular polynomial has at least one root that's in the right half plane, or we have an unstable polynomial coming from s cubed minus 3s plus 2. Suppose we want to look at more information. Suppose we now want to build the Routh array and see what we can tell relative to those poles. Do we have one in the right half plane? Do we have two? How many do we actually have? In this case, it was a cubic. We can build up the Routh array. We have 1. And now we jump over the s squared term, which isn't even there, so now we end up with minus 3. Now in the s squared, we need the coefficient of the s squared term in that polynomial, well, that's 0, and then we skip over the next s term, which is the s term, and we land up on the constant coefficient, which is 2. And now we have in play in our Routh array the situation case B, which is when we have a 0 entry or a 0 element in the left column, and yet we have a non-zero entry somewhere else in that row. So in that case, we're in case B, and we replace that with epsilon. That now allows us to continue the construction of the Routh array. S1 will be now epsilon times minus 3. Let me write that as minus 3 epsilon minus 1 times 2 all over epsilon. And the S0 row, again, we have nothing there, so this comes right down and we have a 2 there. We can now examine this particular left column for sign changes. So let's now look at the left column as epsilon actually approaches 0 from the positive side. So if we look at in the first row, the s cubed row, we have a positive coefficient. S sub 2, that's coming in from the positive side of 0, so S sub 2 row is positive. In the S1 row, as epsilon approaches 0, this particular entry actually vanishes. We have a minus 2 divided by a positive number, so that next term is actually negative, or the next entry in our left column, and then S sub 0's row is positive. And we've looked at this case before. This now tells us that we have two sign changes that result from this Routh array, and how many roots do we have then in the RHP, in the right half plane? Well, if we have two sign changes, we actually have 2 roots in the right half plane. If we wanted to try to determine maybe numerically what we might have, now we could maybe do synthetic division. We have a polynomial of s cubed plus 0s squared minus 3s plus 2, and since we have a 2 as our constant coefficient, we might anticipate that a root might be at minus 2 or plus 2. Suppose we say that we now have a s equal to minus 2 as a root in our synthetic division. We now have the opportunity to try to do this synthetic division. So now I drop down the 1, I multiply 1 times minus 2, I have a minus 2, I add those or combine 0 and minus 2, I have a minus 2, I have minus 2 times minus 2 or a 4, I add that term to get a 1, I have 1 times minus 2, and that's going to give me a minus 2, and I have a 0 here, so that I end up with a 0 remainder. So in fact, s equal to minus 2 does give me a root of that original polynomial. And this is now what has been, what polynomial remains after factoring out a factor that has as a root s equal to minus 2. So this will lead to a factor of s plus 2 in the cubic. This remaining after the synthetic division says I have an s squared minus 2s plus 1, but that, if you see right away, that's now s plus 1 times s minus 1. I'm sorry. I have a minus 2s, so that's an s minus 1 times an s minus 1, and now we can see that the original polynomial, which was s cubed minus 3s plus 2, is in fact factored as an s plus 2, s squared minus 2s plus 1, or that's s plus 2, s minus 1, s minus 1, and there are two roots that are positive, and now we've found, in fact, where those positive roots are located. We didn't have to do that. We kind of just did that for some extra information. We were able to conclude from the Routh array that we did have two roots in the right half plane. And this was case B, where we had a 0 element in the left column and non-zero entries to the right in that row. Let's look at one more example using the Routh array, and here let me just explain where we're headed so that you have some insight, or you can use your intuition as we proceed. But let's look at a symmetry example. And in this case, suppose that we now have 0, or a root of our polynomial at the origin. Suppose we have another root at plus 1, and we have another root at minus 1. And from that, we can actually find a factored form of our polynomial, delta of s. This particular factor will be s minus 0. This will give a factor of s minus 1, and this will give a factor of s plus 1. So that now, if we multiplied those all those factors out, we have s times s minus 1, s plus 1, or s times s squared minus 1, or this is now s cubed minus s. That now we have the background. We know what to expect as an answer. Let's create the Routh array from this particular cubic. We know that it doesn't satisfy the Hurwitz test. We're missing coefficients. We have a negative coefficient. So the Routh array is going to hopefully tell us, or provide us an answer that's consistent with what we know should be happening. We can populate the first two rows of this cubic. We have 1. We don't have a squared power of s, or s squared, so the next term in the s cubed row is minus 1. In the s squared coefficient is 0, the constant coefficient of 0, so now we have an all 0 row, and that says that we need to find our auxiliary equation, a of s, from the row immediately above the all 0 row. Well, that's the s cubed row, and we know then that since it's the s cubed row, one of the leading coefficient is 1. The next term in that polynomial, we skip over a power of s, so we're missing the s squared term, and we have a minus s. That's our auxiliary equation. We differentiate that with respect to s, and we have 3s squared minus 1. These coefficients can now be used to populate the all 0 row. We replace the s squared entry or element with 3. We replace the constant, since we're skipping over powers of s in each column of the rows. This is now going to be replaced with a minus 1. The S1 row is built by taking 3 times minus 1 times minus 1 all over 3, and the S0 entry or row is going to just be the minus 1 brought down because we had this missing element in the S1 row. And what is this particular value? Let me kind of get rid of that to give me some more room. But now we have minus 3 plus 1, or minus 2 over 3. And from that we can now count the number of sign changes. We have positive, positive, negative, negative. We really only have one sign change that results from this Routh array construction. If we have one sign change, then we have one root in the right half plane. Now, how many symmetric roots did we have? Where was our all zero row? So the all zero row allows us to determine how many roots are symmetric with respect to the origin. The S2 row was all 0. That means that we are looking at the row above the S2 row for symmetry, or we now have 3 roots that are symmetric. With respect to the origin. So if you now had 3 roots that are symmetric with respect to the origin, what situations might you have? Well, you might have this, where you now had 1 root at the origin and 2 roots that are purely imaginary, or you might have, let me go ahead and make these roots blue. You might have this case. In the left case, if these roots are at plus and minus JB, and maybe this is at minus A and plus A, which example did we have? Well, if we go back to the Routh array, we actually had one sign change, so we had one root in the right half plane, and that then is only going to happen for this particular pattern of symmetry with respect to the origin. This is actually our example. If we would have concluded or been able to conclude from the Routh array that we had no sign changes, which didn't happen here, then we would have had what the pattern is showing on the left. So here I've just shown the 2 general cases of 3 roots that are symmetric with respect to the origin. They each have a root at the origin, but one on the right has a root in the right half plane, or with a positive real part. The picture on the left has no roots in the right half plane, so we would have had no sign changes for the left pattern, one sign change for the right pattern if we had or started with a cubic polynomial. That should help illustrate the different possible cases. Case A, where we have all non-zero elements in the left column. Case B, where we have to introduce an epsilon. That was in our third example that we illustrated. And we had 2 examples that illustrate the situation, case 3 or case C, where we have an all 0 row, and when we have an all 0 row, we have symmetry with respect to the origin, and that symmetry is determined by the row immediately above the all 0 row. And I hope that that now helps you with these examples better understand the Routh array and how it can be used to tell you how many roots are on the imaginary axis, how many roots are in the right half plane, and how many roots are in the left half plane.